Now we understand a bit about security, and the next topic will be more on the AI space and machine learning. So I would like to introduce our next speaker, Deepak Shankar, Chief Environmentalist System Modeling at Mirabilis Design. So Deepak is an early proponent of system modeling and has been involved in the development of marketing and system modeling since 1993. Deepak is an electronic engineer with a bachelor from Coimbatore Institute of Technology in India and master from Clemson University, USA. He also has an MBA from the University of California, Berkeley. He's currently Chief Evangelist at Mirabilis Design, of which he was the founder. He started his career in the Alta group of Cadence, where he went from support engineer, application development, and finally marketing. So he will speak about Silicon IP solutions for the AI connected world. No, sorry. My mistake. What? My mistake. So, architecture exploration of AI machine learning implementation on processors, GPU, CPU, FPGA, and accelerators.
Okay. Hi everybody. I think I'm the last speaker before lunch, so I'll keep it really long so you feel sufficiently hungry before you get to your food. So thanks a lot for the introduction. I thought it was like Mickey Mouse singing. But no, I didn't even do that. Okay, today I'm going to talk about artificial intelligence and machine learning and how you can implement it. Now, one of the things that I try to do in this presentation, which may not cover in detail any one topic, is that we're looking at artificial intelligence and machine learning not just from a perspective of creating a new SoC or a new processor, but looking at it from the customer's standpoint, meaning the end user, which can be a data center, edge device, or someone that's building the accelerators in an existing SoC that can also be that can also have the artificial intelligence built into it. So that's one of the reasons why we looked at not just the creating a very specific AI process, but also looking at general purpose things of using x86 would be more software driven to GPUs, which is how the learning systems are currently almost 100% implemented. Quick introduction about the company. Mirabilis Design has been around since 2003. We've been responsible for helping companies develop a whole variety of electronics ranging from x86 processors to SSD controllers to completely connected electronic warfare for humans to automotive networks. We've been involved in working with a whole variety of application segments ranging from defense electronics to automotive to semiconductors. The product itself that we're dealing with, and I'll show you some of the designs that we've done around artificial intelligence, is called Visual Sim Architect, and it's a system level modeling and simulation software. For those of you unfamiliar with the space, it's where you create a prototype in software of a proposed system. And again, system could mean just the AI processor, or it could be a controller or interface, or it can be an end-to-end system where some of the processing is done at the edge and the rest of it is done in the Google Cloud, for example, or in Azure Cloud. The main reason for system modeling to be very critical is that you get to visualize and be able to experiment with different scenarios before you invest a huge sum of money, and then the right before delivery you find issues or bugs that have to be fixed. So you kind of weed out all those issues. Now, talking specifically about the basic definitions that go into architecture exploration. So I wanted to cover this before I get into the AI. The reason being that some of these terms may or may not be new to some of you. People that have already done modeling, this is not new. The main thing is with artificial intelligence, there's a lot of unknowns. So before you even start saying, okay, I'm going to build an AI processor, I'm going to incorporate AI into the edge, it's really trying to understand what the specification is. What is it that is required of you? And that is where system modeling comes in. Think about it as a nice task graph of something that you would do while stock trading, right? What is the sequence of things you're going to do? Now, within that, what are all the resource requirements? You can take simply, I've got so much of compute, I've got so much of storage, I've got so much of memory processing, which if you look at a little more detail, then you say, okay, now let me start putting the logic into each one of those pieces of task graph. So that's in a sense what architecture exploration is all about. Now, architecture exploration gets split up into multiple different segments. So one of them is what's called functional correctness, which is, am I having any deadlocks as a result of, say, a mutex or priority inversion, to all the way to looking at how much time does it take to complete this thing, to how much of power is going to be consumed, because if I'm sitting at the data center, I've got operational cost. If I'm sitting at the edge device, I've got a low quality product. So I've got to bridge the gap between performance and power consumption. So that's a key critical factor. Finally, one of the things that we're finding with all connected devices, and I know our gentleman Jonathan from Winborn just spoke about security. One of the aspects of security is being able to analyze the failures. What would happen in your system if, say, one of the failures happen? And failure doesn't mean a complete breakdown of your system. A failure can be where we're having an error in a schedule table in the memory, or for example, one of the codes slows down, or there's just network congestion to get the sensor data. So all of these need to be put together to create a high quality product. Now, looking specifically at the processing requirements at AI, there is AI at different levels. There's one at the host, there's one on the network, and then there's one at the data center. So if you look at the host, there's all the sensors. There's the processing of the sensors. It could be filtering, it could be more intelligent data tracking. And so you can take decisions such as, do I do all the processing there, or just send everything to the cloud and get data back? Which one's better? Again, it depends on the application. Just like my economics professor says, is this good or this bad? It depends. Same thing over here. Same thing on the network. If I send these messages as small bursts, or do I send them as big messages? How do they impact? Notice there's no AI there, but all of these extraneous factors impact your AI system. So when you say I'm going to design an AI system, it's not just the accelerators, not just the matrix multipliers, not just the buffers, not just the memory access. It's all of these have to be considered when you're designing your AI system. Now, I'm going to take up one simple example. This one here is a network system. Now, this could be a single chip, or it can be completely distributed across a car, and it's a braking system in the vehicle. What I have is I've got all the four wheels. I got a variety of sensors. I've got here like road condition, proximity, the manual braking, gyro, the engine rotations, all of those that come together into one ECU. Now, the simple questions are, how much time does it take to complete the processing of this braking action, which is based on the road condition and proximity sensor determines how fast the vehicle should be running. But at the same time, what if there's an error where the road condition sensor misguides the numbers and puts in a different value? What happens here when the user has to manually intervene and try to brake? You notice that because of the proximity sensor getting higher priority, if you look at the line number 6, which is right down here, you notice that even though the users manually brake, the system's continuing to run because the proximity sensor has higher priority and has mutex, so it cannot be preempted. So it's when you're actually designing the AI system, you should also take into consideration what is the flow, which is what I call the task graph. Understand what's the processing for each one and be able to incorporate all of that into your analysis. Now, if I take a cloud, the biggest thing is when I look at the local devices, there's going to be power consumption. There's going to be a battery. So how much of processing can I put into that and not kill my battery to all the activity happening on the network. I could have network failures as you see down here. I could have multiple hubs that are located all over the place. And finally in the data center, which could be where all the real processing is taking place. How does that differ from my earlier scenario where everything was happening within the car? What is the processing requirement? Now, even in a car, you can say that I'm not going to do the processing there, I'm going to set it up the 5G network, go into the cloud and come back. So is that better? Could that increase my accuracy? Which one would be a better option? There are constraints in terms of power and performance to facilitate that. Now, the other piece of it is now that you've seen the whole network, seen the edge, seen the data center, seen all of it, let's narrow it down to the actual custom processing. So in this particular case, we're focusing more on a warp-based architecture, so more of a GPU type architecture with more specialized instructions, which is that G block you see there, but a variation in terms of how the memories are handled. So in terms of, rather than having a buffer and then the memory, here it's like alignment of multiple blocks of cache that handle the data coming in. So you have separate cores of threads, and you can see down here, it shows me the latency for all the different cores. So what this gives me how I can parallelize my entire system as opposed to the earlier situation, which is one at a time. So it's like, there are certain scenarios where, doing a sequential processing is okay, but here where you're doing more of, like time sensitive, the concurrent processing is more important. Now, a quick introduction to the product. I'm not going to go into detail. Anyone wants to know can come over to our booth, which is all the way on the other side. But really, what you need for this is a Monte Carlo simulation where you can run hardware-software partitioning, like power performance trade-offs, looking at the failure analysis, but be able to incorporate everything. So even if you take an SoC, which is an AI processor, it's got interfaces, it's got software, it's got hardware. How do you incorporate all of that to design your AI system or AI chip itself? I'm not going to go in detail, but just show you these are all the kinds of IPs that you require to really put the whole system together. So it's not just here's one block, I just need to know this one functionality, or here's two blocks, but rather there's probably about 60 to 70 different components that you require to assemble the modeling of an AI system. So only if all of these are there, you can do a complete job of looking at the overall design. Now, let's come back to why system modeling. We talked about this a little bit, but the main thing is really you want to go from soup to nuts in a same platform. What that means is conceptually, does this make sense? Putting it into a detailed architecture that needs to be implemented. Sharing with customers early in the design process. Start getting early software feedback so your customers can start designing the software that needs to go on the system, or custom accelerator functions that need to go on your system. Being able to do that with a single platform, so you're not like bits and pieces trying to assemble things up. The other one is the second last one here, which is storage and cache memory hierarchy. Because even with accelerators and even with concurrent operations happening, the cache memory hierarchy is still your major bottleneck. And if anyone here from high performance computing can validate the thing that's where most of your bottleneck is. All you need is slightly little more cache, and you might get much better performance without even having to change anything else. So that's a major consideration here when you're doing system modeling, is looking at what is the minimum I need to do so that I can get an AI processor out. Now, again, not going into detail, but just to show you, these are all the different things you need in a system modeling environment to be able to, be able to say, this is the total solution. So anything from the processor module components, the peripherals, the memory devices, defining the most important thing here is these two components. Traffic. What is the rate at which the requests are coming in? What is the rate at which the sensors feeding data in? That's one piece of it. Second piece of it, what happens to the data as it flows through your system? You can call it use cases, you can call it task graphs, variety of names that are used. The reason we don't use the word software is because some of it can be accelerated, some of them can be done in software, some of them can be just data movement. So it's really a flow. Being able to describe both of these is very, very critical in being able to do your architecture exploration. Of course, having good analysis tools always help. It's like having GDB, for any software development. Now, a lot of the stuff might not be new to you, but really, looking at impact of emerging technologies, which is incorporating, say, a concept of GPU with just a few accelerators. Is that sufficient for your AI? Or, as like a number of companies like Wake Computing and Nutanix, which has just come out, and a number of others, that are coming with dramatically different architectures. Some of them are even providing analog engines. So rather than doing everything in digital, everything is done in analog. So gets you higher performance, or actually with the analog engine gets you significantly lower power consumption. Is that the way out? And looking at what are the challenges that you have to affect. And again, I'm going to stress on memory access, the sensor inputs, and also all the connected devices, all the communication between all of them. Now, one of the things is a lot of these AI is going into products that require certification. Functional safety is one of them, hardware-software interaction in aircrafts and in defense systems with DO-254 play a significant role. One of the things that we've been seeing a lot in this industry is people don't want to wait until a prototype's available before they can study functional safety. They should start providing data to the NTSB or the FAA or any of the other certification agencies well before the product's available. Only way to do that is to have an active prototyping environment where they can get virtually the whole design, understand what's happening from end to end. And that's a huge impact on the success of your product, because one functional safety failure can push you back by 2 years, push you back even by 3 years. And that's something that needs to be considered right up front. So levels of abstraction, if you look at each one of those host data centers and the box design, you can see there is like the hosts, what are the host rates that you need to worry about, which is typically your traffic, sensors, latencies, throughput. But then the biggest one is, if you look at, is that the data centers, which is your delay of your hardware, the max, the warp conditions, and your memories in FIFOs. So I'm just going to show you a few examples. This one is where you've got a host to data center on like an edge device, and you can see the important thing right in the middle on the top right over there is the battery. How do I keep the battery life, which is, you're looking at the latency over here to the data center with the MIPS that you're getting, but all the way on the top right shows you all the functionality that's happening, to keep the same battery running. x86, this is something that's purely in software. You can see, like because of the processor's inherent ability of going to caches and going to memories and having shared resources of like multi-cores and things like that, the latency is all over the place. It's not like a fixed, it's not like very, within a small band. It's really a wide-ranging thing. Slightly better, you can look at the latencies. It's not as bad as the earlier one, but still, because it's a general purpose processor, you get to see the latency is still in a broad range when you go with an ARM-based SoC. x86 ARM, not a whole lot of difference. Yeah, there's some differences in power, some differences in performance, but the main thing is this tends to be a little more focused with having accelerators and things like that. FPGA is another solution. A lot of people have been using it for a while now. It works very well, especially with the high-speed interface between them and putting multiple FPGAs together. And of course the GPUs. Again, if you notice, the GPUs have a very tight latency range. So if latency is very important, and that's a critical factor, that's why a lot of the learning and even a lot of the inference systems are using using GPUs because of that very tight range, and also because of the power consumption you're looking at. And of course, now we have tensor processing. This is version 1. And then you have version 3 in the cloud, which is this is the latest one from Google. And you can see how the difference in the power plots are, and how it's more. It's becoming a narrow and narrow belt when you're getting results back. This is again model not with very detailed information. It's modeled just with publicly available data because Google has still not provided all the information on the TPU 3.0. The 1.0 has a lot more information. With this, thanks a lot for the time, and I'll be open to answering any questions.